First, let's define our system. The system here in this case will be the Earth plus the mass that is somewhere above its surface. So we can say that's the surface of the Earth. Here is the mass. It's given to be 4 kgs. Its initial speed is 0, and it is 10 meters above the surface. So this is our system. So everything that's just the Earth and this mass is our system. Anything that's not the Earth or that mass is not part of our system. Put it like this. So what we are asked is we need to calculate the potential energy of the system when, if we take this to be a y component, so when y is equals to 10 meters, y is equals to 5 meters, so the mass has dropped already some distance, and y is equals to 0 meters. So right before, just that instant before the mass hits the Earth and comes to rest. Now, we also, in the second part, we are asked to calculate the kinetic energy of the system for the same configurations. So when y is equals to 10 meters, y is equals to 5 meters, y is equals to 0 meters. Now remember, when we refer to the system, we mean we want the potential and kinetic energy for every object in our system. So you need to think about what the Earth is going to be doing in this problem as opposed to the mass. So let's start by looking at the kinetic energy, say, that the Earth would have. So would the Earth gain kinetic energy as the mass falls? So, because from Newton's third law, we know that the mass is attracted to the Earth by a force Fg, which means the Earth must also be attracted to the mass by a force Fg upwards. So there's a force on the Earth, but would it change, would it gain kinetic energy? In theory, yes, it would, because unbalanced force implies acceleration. But let's just have a look at what that acceleration would be. So the acceleration of the Earth would be equals to this force Fg times the mass of the Earth, which would be equals to 4 kilograms in this case, times 9.8, divided by the mass of the Earth. Now the mass of the Earth is quite large, and compared to a 4 kilogram mass, we can assume that the Earth is almost an infinitely large mass. So we can say the acceleration of the Earth is approximately equals to the limit where the mass of the Earth goes to infinity of this expression Fg over me, which is equals to 0. Any number you divide by an infinitely large number gives you 0. So to a very good approximation, that is true, right? Because the Earth has got so much mass to begin with. So if the Earth has got, to a good approximation, 0 acceleration, it means the Earth cannot gain kinetic energy, because the velocity of the Earth, we assume we're working in a frame where the Earth has got no velocity to begin with. No acceleration means no change in velocity. No change in velocity means no gain in kinetic energy. If we assume we can define a frame in which the Earth is at rest, it will remain in rest in that frame for the entire problem. So the kinetic energy of the Earth will always be 0. So kinetic energy for the Earth is 0. And this also now restricts the potential energy, because now the Earth has no potential to gain kinetic energy, right? Because it has kinetic energy equals to 0. It's not really being accelerated, so no matter where I place the Earth, it's got 0 potential to gain kinetic energy. Therefore, the potential energy of the Earth in this particular setup is 0. So if we look at our system, it means that the potential energy of our system is, at any point, it will be equals to the potential energy of the 4 kilogram mass, and the kinetic energy of our system will be equals to the kinetic energy of the mass. Right? Because the Earth has got 0 potential energy, 0 kinetic energy in this problem, because it's so small compared to that mass. If this were 2 planets interacting, we couldn't make that assumption. Right, now let's look at the potential energy for y is equals to 10 meters. Then the potential energy of the mass is equals to m times g times 10 meters. We derived this yesterday, just an expression for gravitational potential energy. It's mass times gravitational acceleration times vertical height above the surface of the Earth. And if you work that out, you find that it is 392 joules. Remember, this is 4 kilograms, that is 9.8 meters per second squared. So if you just multiply out, that's the potential energy of the mass. And if it starts out at 10 meters above the surface of the Earth, its kinetic energy, if its velocity is assumed to be 0, we know that the kinetic energy of this mass is going to be 0. Now, when the mass is 5 meters above the surface of the Earth, its potential energy becomes mg times 5 meters, and this is 196 joules. It's just half of that. Now the kinetic energy, well, let's first look at the change in kinetic energy of the mass. We know this is equals to the work done on the mass itself. That was what the kinetic energy theorem told us. You've got a single force acting on an object, and the only change that that force can bring about is a change in speed or velocity. Then we know that the amount of work done on that object is equal to its change in kinetic energy. Now the work done on the object is just equals to, there's only one force acting on this object, it's its weight. So the force is going to be Fg dot displacement. Let's call it delta y. Now if I set up an x-y axis like this, the force weight will point downwards, so I get negative m times g in the y direction, and my displacement would also be downwards because it starts from there and it ends up there, so it's negative 5 meters also in the j direction, dot in between them, because I end up 5 meters below where the mass started. And this is just then mg times 5 meters, which is 196 joules. Okay, and the last one is for this up a bit. So for y equals 0 meters, we know the potential energy of the mass is just going to be 0 because it's now 0 meters above the surface of the Earth. Sorry, by the way, our change in kinetic energy is K final minus K initial. Since this is equals to 0 for the mass, we've got that this is just equals to K final. So we can get the kinetic energy of the system at that point. We do now the same for y is equals to 0. Again, we know the change in kinetic energy, just going to divide that. So the change in kinetic energy is equals to the total work done. This is again equals to negative mg along the j direction dot with negative 10 meters along the j direction, because this mass has now fallen all of 10 meters downwards. So the displacement is downwards, the force is downwards, so we expect positive work to be done. And what we find is indeed, yes, we get positive work done equals to mg times 10 meters, which is equals to 392 joules. And we know this will then be equals to K final, because initially this mass was at rest. Okay, so we've calculated the potential energies and the kinetic energies of the entire system now for a couple of different points in the motion. And the next question is, what is the sum of the system kinetic energy and the system potential energy at every single point? So what we need to answer is, what is the sum of the potential energy of the system plus the kinetic energy of the system at, or rather when y is equals to 10 meters, when y is equals to 5 meters, and when y is equals to 0 meters. Now, from our previous slides, here we've got that the potential energy was 392 joules plus 0 kinetic energy. So that's the potential energy, that's the kinetic energy, which is just equals to 392 joules. Here we had that the potential energy was 196 joules, and we had that the kinetic energy was also 196 joules. So the answer we get if we add the total potential energy and the total kinetic energy together is again 392 joules. And over here we had no potential energy, just kinetic energy, which again gives us the same number. So if I were to just look at this, it would seem, so can we draw the following conclusion? So let's look at what we had. We had an isolated system. The only force acting on this was the force between the Earth and the mass. So it's a force between two objects in the system, so it's an internal force. So we had an isolated system, so nothing from outside the system affected the motion. And we had a conservative internal force. So this is a force from one object in our system on another object in the system. So that's just what internal force is. It's always forces between things inside the system. What this would suggest is that if I define the mechanical energy as m, and I say this is equals to the potential energy at any point plus the kinetic energy at any point, that this is equals to a constant. Right? Because it doesn't matter when we looked at this system, every time if we add potential and kinetic energy, we get the same number. Another way to state this is that the change in the mechanical energy between one point and another in time is equals to the change in potential energy plus the change in kinetic energy, and this is equals to 0, because we had no change in the mechanical energy with time. Okay, so it seems like we have got a conclusion here. If we've got an isolated system, there's only internal conservative forces acting on that or affecting the motion. The total energy, which is now all the kinetic energies plus all the potential energies of that system, will be a constant. Right? So it tells us under which conditions mechanical energy is going to be conserved. So whatever amount the mechanical energy of the system had at the beginning, if it's got only internal forces, these forces are conservative, it will keep that amount of mechanical energy forever and ever and ever. Now let's see how general this is